Hello everyone, welcome to this video. I hope you're all doing good. Again, we'll be continuing with this ISI preparation series. I hope you're following it with all your heart. Um, this will be probably the last lecture on number theory, arithmetic functions. It is not really used that much, but sometimes it is playfully asked, maybe not in UGB, but in UGA definitely, in different forms, especially since we are dealing with multi-choice corrects. But today we'll be solving in subjective forms only. We will be understanding what arithmetic functions are, what multiplicative functions are, and we will be basing our questions purely on that. All right. So we'll solve mainly questions dealing with multiplicative functions, and you'll understand why it is so important. What is a multiplicative function, first of all, if you may ask me, then I'll tell you. A multiplicative function, arithmetic function is first of all, it is dealing with integers, right? Arithmetic operations on integers. Now, if it is what is a multiplicative function? Multiplicative function. This function is, let's say, f of n. This is from n to n. This is defined such that f of mn equals to f of m into f of n whenever if the GCD of m comma n is 1. If m and n are co-prime, then it follows this property. This kind of functions are called multiplicative functions. Okay, so what is the first question? Let G be an arithmetical function defined for each n greater than or equal to 1. By this, so G of n is defined. Each integer can be, categorized among 0 mod 3, 1 mod 3, 2 mod 3. So if it is 0 mod 3, it is 1, 1 mod 3, 2, and so on and so forth. Okay, so is this a multiplicative function? Huh. So first of all, the characteristic of a multiplicative function is that since it takes only non-zero values, it takes only values in natural numbers, because it is an arithmetical function. That means the domain and codomain both are n only. Okay. Now, what does that mean? G of n is never zero. So G of n is equal to G of n into 1, which will be equal to G of n into G of 1. So that will imply that G of 1 has to be 1 always if it is multiplicative. Yeah, if G is multiplicative. Okay, so what does that mean? What is G of 1 but it is equal to 2, as 1 is congruent to 1 mod 3, obviously, right? So that implies G of 1 is 2. So this immediately tells me that this is not a multiplicative function. Got it? So G of 1 for a multiplicative function, this is another important thing which you can, weigh with, is that a multiplicative function at 1 must be equal to. Now, if you want to check it in some other way, let's say G of 2 into 3 should be G of 2 into G of 3. But what is G of 2? What is G of 6? Is it equal to G of 2 into G of 3? Let's check this. What is G of 6? Because it is 0 mod 3, this will be 1. What is G of 2? G of 2 is 2 mod 3, so it will be 3. And G of 3 is 0 mod 3, so it will be 1. So this is again creating a problem, not possible. Right? Therefore, G is not multiplicative. Can there be multiplicative functions? Definitely there can be multiplicative functions. But let us assume this also. Now let's look at this question. Does there exist a multiplicative function such that this happens? And what can we do? This is basically we want to try and factorize these things. Why? So let's see. 30 is 6 into 5, so that is 2 into 3 into 5. 105 is 3 into 3 into 15, is it? No, no, no. 3 into 21. No, it is 3 into 35. Ah, 3 into 35. So 3 into 7 into 5. So I'm thinking 5 into 21. I don't know. I just messed it up. Okay. 70 is 7 into 10. So 2 into 5 into 7. This is there. So that means f of 2 into f of 3 into f of 5 is 0. F of 3, this is the first one. Second one, f of 3 into f of 7 into f of 5 is 1. Thirdly, f of 2, f of 5, f of 7 is equal to 1. Please note that these two will imply clearly that f of 2 cannot be 0, f of 3 cannot be 0, f of 5 cannot be 0. See that? So how can the product be 0? How is this possible? This is impossible, not possible. So again, f is not a multiplicative function. This implies f is not a multiplicative function. Okay, that's it. Okay, read this question. Here, we are already given that f is a multiplicative function, and then we have to prove that another function which is related to f, wait a minute, is related to f has to be a multiplicative function as well. This looks like a very simple question, but it's not. It's not as simple as you might think. Okay. Now you see, what can we do about this? Right? F of k n by f of k. F is a multiplicative function. So when can I write f of kn as f of k into f of n? I want to do that, but it's not possible. This is not possible because k and n need not be GCD 1, right? Kn need not be 1. This is not necessary. Okay. So what do we do? I take factors of k which are related to n. I can write k as, k can be written as kn into uh, km, I guess, something else basically. So I can write kn. Kn is the uh, part of k which is common with n, right? So basically what is happening, km comma n is 1. So what is happening here? I can write and also kn comma km is 1. Okay. So I can write fkn as f of kn into km into n. So you see that these two have common stuff. So I'll write it like f of kn into n into kn. These two are GCD 1. So I can write this as f of kn n f of km. You understand? And what is f of k? F of k also I can write it as f of kn into km. Since kn and km also have 1, right? Do you understand what I'm trying to do? I'm trying to take the common part, the part of k which is having something common with n separately, and which has nothing to do with n separately as km. Now I'm just separating those two so that I'll have some sort of ease in calculation. So this is kn into f of kn. So now what happens? What is g of n? This becomes f of kn n, f of km by f of kn f of km. Now you see that we can cancel this out because we're only taking from n to n, which is not written here, but yeah, we are only taking n to n, and this can be f of knn by f of kn. So this is for each n. I can figure it out for each n. I can, so for each n, we will have part of k which is totally common with n, and we'll have part of k which is not at all common with n, and the not at all common part is getting cancelled out in the numerator and denominator. Right? Now let us assume, now what do we need to show? We want to show GCD, or rather G of AB is equal to G of A into G of B. Right? This is what we want to show, where uh, A comma B, the GCD of A comma B is given to be 1. Now what is G of A? It will be f of Ka by f of k. If you understood what I did before, I can write k as some Ka into Km again, so that this will be, K is the part common with A, which has common factors with A, nothing common with A. So what is basically happening again? I'll repeat it again. So Ka comma Km is 1, Km comma A is 1. So we can write this as K into A by f of K. And similarly, I can have G of B as f of KB comma B by f of KB, right? Now what happens with f of, you know, G of AB? If we have G of AB, then I have to get something like, f of K AB by f of K. Here what do I do is that I'll write K as Ka, Kb into Kc, something like this. Because A comma B are anyways GCD1, so these two are going to be anyway separate. A and B don't have anything in common, so K and KB also won't have anything in common. So we don't have any problem in writing like this. So Ka comma Kb is going to be GCD1, Kb comma Kc is going to be GCD1, Kc comma Ka is going to be GCD1. So there is no problem at all. So we will be easily be able to write K, Kb, Kc, Ab by f of Ka, Kb, Kc. All right. So this can be written as, oh shit, there's not much time. So f of K into A, f of Kb into B into f of Kc divided by f of K, f of Kb, f of Kc. This will get cancelled, and you'll see that this is obviously g of A into g of B. It is the same Ka, Kb which we got above. The Km is different. The Km is different. Okay. So this is how you have to think when we are talking about multiplicative functions. So I hope this made sense. All right. Now the next question will be even more mind blowing if you enjoyed this question. If you enjoyed this one, if you have any doubts, please drop that down in the comments. Um, so I'm just taking the common part out, non-common part out, and I'm just separating them so that The multiplicative part. So what is important in multiplicative? The GCD 1 part, right? Wherever the GCD is 1, we can separate them. The multiplicative property can be utilized. Okay. F from n to n be a strictly increasing function such that f of 2 is equal to 2. And this is a multiplicative function wherever they are relatively prime. This can be written like this. Show that f is an identity function, that is f of n equal to n for each n greater than or equal to. Okay. F of n plus 1 is strictly greater than f of n, right? This is what strictly increasing function means. This means f of n plus 1 is strictly greater than or equal to f of n plus 1, right? So can I prove inductively, since f of 1 is equal to 1, can I inductively prove that uh, that would that mean f of 2 is greater than or equal to 2, and say f of k is greater than or equal to k, that would imply f of k plus 1 is greater than or equal to f of k plus 1, which is greater than or equal to k plus 1. So can I prove that therefore f of n is greater than or equal to n? This is true for all n greater than or equal to 1. Is this clear? Inductive step. This is a so this is inductive presumption, and then this is the inductive step, and then yeah, everything is proved, right? Mm, nice. If we get this, I think we can we find f of 3? Hmm? What is f of 3? F of 2 plus 1. So it is okay. It is greater than or equal to 3. That is fine. But what can we do with f of 3? F of Oh, do we have f of 1 equal to 1? By the way, you have to notice that. Where did I get this one? F of 1 equal to 1. Because, I didn't prove it. F of 2 is equal to f of 2 into 1 is equal to f of 2 into f of 1. So f of 1 always has to be 1. You know, in any multiplicative function, you can take it for granted that f of 1 has to be 1. So what do we do with this? What do we do with f of 3? Hmm. Okay, just a minute. I think there is some. Okay, just okay. So if we get an inequality from the other side for f of 3, let's say okay, 15 is less than 18, or rather 15 is less than 20. So f of 15 is less than f of 20 because f is an increasing function. This will imply f of 3 into f of 5 is less than okay, rather I would rather write it as 18 less than 20. Both should come. I think that is important because otherwise I cannot separate. So f of 18 less than f of 20. Okay. So what is happening? F of 3 into f of 5 is less than f of 2 into f of 9, right? And 9 is less than 10. This will give me that f of 9 is less than f of 2 into f of 5, and this will be less than f of 2 square into f of 5, and we know that f of 2 is 4, and I can cancel out f of 5. So you have that f of 3 is less than f of 2 square, which is 2 square, which is 4. f of 3 is less than 4 and f of 3 is greater than or equal to 3, our initial thing. Wow. So this gives me a strict inequality which gives me f of 3 is equal to 3 is the only way possible. Okay. Now tell me something. What is f of 6? What is f of 6? This is f of 2 into 3, f of 2 into f of 3, which is equal to 6. Right? So f of 3 is equal to 3, f of 6 is equal to 6. That means between 3 and 6, what happens to the rest of the values? Yeah. So do you see that these have to be equally distributed with all the outcome values between 3 and 6 as well? Yeah. Right. I mean, because f is a strictly increasing function. So I'll write it down like this. F of 3 has to be strictly less than f of 4, less than f of 5, less than f of 6. Right, and these are taking only integer values. This is 3 less than f of 4 less than f of 5 less than 6. So what are the possible integer values? 4 and 5 only. So f of 4 has to be 4, f of 5 has to be 5. Okay. The moment I have f of 5 equal to 5, what is f of 10? What is f of 10? F of 2 into 5, so it is f of 2 into f of 5. So this has to be 10 again. So again, between f of 5 and f of 10 is has to take, 6, 7, 8, 9. These have to be there. If this is 5, this is 10. So do you see the pattern? This means this has to be f of 9. So f of 9 is equal to 9. So I'll again get f of 18 is equal to 18. This implies between 18. So again, this will imply f of 17 is equal to 70. So f of 34 is equal to 34. And then f of 33 is equal to f of 33 is equal to 33. So you see the pattern? The idea is that if you get one odd number, let's say n is an odd number, such that f of n is equal to n. Then f of 2n is equal to f of 2 into f of n, because always known that 2 comma n with an odd number, there is no common divisor with 2. So this is equal to 2n. This implies between n, f of n less than f of n plus 1 and so on till f of 2n minus 1, f of 2n. This is equal to 2n. This is equal to n. The only possible values, because it is strictly increasing, is that this must have the value 2n minus 1. So by this inductively, we can keep on going with these values. I hope you see that this forces our function to be an identity function. This forces our function to be an identity function. So I hope that was clear. I hope you got something to learn from this video. And that's pretty much it. Take care. Tata. Bye bye.